All right, so here I'm beginning with video number one. I think I'm probably going to do these in like groups of like two. I don't know. These first two problems, I don't think I'll need to spend much time on them. So I think maybe I'll do the first four, and then I'll send some other videos for the other ones. So I can see where he's building up with this stuff. It seems like it's logically uh, organized. The assignment kind of leads you through some bigger ideas, but I don't know what the depth of those ideas is really going to be. I think he's like, it's intermediate depth, I think. Because you can tell he's coming up with some bigger concepts that are going to be probably introduced later. But that said, I don't want this to be like a super long video. And I don't think you want a super long video right now because you're probably, I know you have the test on Monday. So, I'm just going to go over the necessary things and just enough depth that I think you can actually understand what's going on without going overboard with that. So I guess let's go with the first question. The first and second question look pretty similar. They're both use Gauss-Jordan elimination to determine whether that matrix is invertible. Like I said, later on you'll learn the determinant. That's a shortcut. It makes a lot of things easier because you can figure out if a system is invertible or not, and that'll be really important later on the whole class. But for right now, the way to figure this out is really just to say, okay, so we're setting this up. This is essentially saying, this bar right here is kind of like showing you what. I mean, by this point, I guess you probably kind of understand how the Gauss-Jordan thing works. You augment the matrix, and this is like saying that A times A to the minus first equals identity. This little cash register bar right here is like saying, it's like this times something, and here's a result, right? So, and then you change it up so that it's like, identity times something equals whatever that is, right? So essentially, this is kind of the operation that you have going here. It's kind of like a number. It's like if you say, A times B, and those are both scalars, A times B equals 1. So 1 is the identity in scalars, right? Or you could even make the argument that they're 0 or one-dimensional. Really one-dimensional. It's the number line, so they're really one-dimensional vectors, sort of, right? And, if you have like A times, assume A is a number, multiply it by something and you get 1, you know that you have the multiplicative inverse. There's only one multiplicative inverse in both linear algebra and in scalar algebra, right? Actually, there's really only one inverse in all algebras. It's kind of a thing that happens in group theory. But yeah, so you know that it's always going to be a unique inverse. There's only one, and the inverse is the inverse of the inverse, which sounds kind of stupid and pointless to mention, but it actually is important because then you'll have the question later on. I'm sure you'll have a question. You might even have a proof on your homework later on where he says, like, prove that if B is the inverse of A, then A is B inverse, right? So, and then you just have to show that A inverse is A. So yeah, that's some theory there, but long story short, the first one you should get, as you can see on the assignment that I sent you, it's invertible, and that's because you don't have a group of zeros. You can, long story short, you can compute the inverse, and you don't get some weird row of zeros, and you don't get any. So if you go to get a row of zeros on this side, then you end up with problems because you'll see on the next problem here. So here's problem 2, right? With this one, you end up getting a logical contradiction right here. Because if you consider each of these rows to be a vector, right? Because they're just rows of columns or columns of rows. And column vectors and row vectors are the columns and rows, right? So think of each of these as a vector on its own, right? So essentially what you're saying is 0 times x1 plus 0 times x2 plus 0 times x3 is equal to negative 3. Well, 0 times anything is 0, so you have contradiction there, there, and there. So that, so the second problem, it's not invertible. You get this row of zeros. You don't have to augment it initially if you want to do that, but just to take out the middleman, it's kind of useful to just throw it in like that. So that's that. Another thing to notice, I think, well, no, not right now. That's something for later on. Another note. I used a different notation here, and that's because I got used to using the superscript subscript notation, and now I can't work through the problems without hitting. I don't know. It's just I'm used to that, so those aren't exponents. No exponents are in this, and but it shouldn't be that important because I wasn't really writing. There aren't too many things where you have to like label the rows and columns. So that's. But just a note there, just so it just doesn't get confusing. If you ever see an exponent, it's not an exponent, it's a superscript. Superscripts are for, you know, well, I won't get too far into that, but yeah, you'll see how it works. So here we augment the matrix with the 0 vector. We don't actually have to do that. He says at the beginning, compute the row echelon form, right? So in order to compute the row echelon form, you can actually do it without setting it equal to a vector, because the row echelon form really is something of the matrix itself. It's a linear map, and if you can get to row echelon form, it's invertible. If you can't, it's not invertible. This one ends up being rank 2, and it's so obviously not invertible. You've got 2 here. The same number of 0 rows, that will be the same as the number of free parameters or free variables. So you can see, without going into the computation, you crunch through all those. You end up saying, okay, so these 2 are pivots, right? Those ones are, and then these ones, obviously, because if you write out the equations, you can say that they all kind of work together. It's kind of arbitrary. It's just a product of the way that you solve row echelon, which ones end up being free and which ones don't, because officially you could, the point is that as you set one of these, the other ones act as dependent variables on it. So if you vary y, it's kind of like if you have x plus y equals 1, you can vary y or you can vary x. But whichever one you vary, the other one will have to vary accordingly to keep the equation true, right? And that's kind of what happens with all of these. And you can see that they always have to equal 0, right? You have to have that for a free parameter. And the reason that that's true is because you have to have, I also don't want to go too far into that right now. But long story short, pivots, these are your pivot columns. These are your free variables, or pivot variables and free variables, free parameters, they call them sometimes. So let's see. So what else there? This is kind of the form of these things. You end up with 2 free variables, x. In this case, it's going to be x3 and x4, right? So don't let this throw you. People do this a lot. You can just consider these to be x's, really. The idea is that the x is actual, like, set in stone, the dimensions. It's kind of like the structure, and these are values that vary along that structure. So let's say you have a plane. The x values are like the frame of the plane or whatever. And then the s values are, it really is just a mathematical tool for saying, oh, well, we can vary it. But it's all kind of semantics. It's just a convention. When people do that substitution, it's the same as saying it's x, honestly. It's pretty much the same thing. There you can see the superscripts. Those are not exponents, they're superscripts. Okay, so that worked out with, okay, so here we also have something called the null space, as you know. I think you said you talked about that a little bit. And this is problem 4 or 3. Wait, this is problem 3, I think, right? Oh, geez, it's the same matrix for both of them. This is problem 3. Okay, so with problem 3, you have that ax equals 0. Okay, so an important thing to remember is, and this doesn't pop up in scalars, there's no null space besides 0 in scalars, right? If you multiply a number by something and it equals 0, that number has to be 0. That's the zero product property. Well, the zero product property also, in a way, it exists here, but there are also, if it's not an invertible matrix, that also means, you'll talk about this, the determinant equals 0. It means that it's smashing parts of vectors into 0. It's like multiplying by 0. And it's a product of the fact that you have multi-dimensional things going on. So essentially, that's kind of what you're finding here, is if you have an invertible matrix, if you can find row echelon form, the null space will only be the 0 vector. The only thing you can multiply by it to get 0 vector is the 0 vector itself. If it's not invertible, there will always be null space. And so, unless, well, no, if it's not, it depends. It does depend. If you are going into a higher dimension, which will come up later in here, there's not null space necessarily. And as a matter of fact, I don't think there ever is null space. I'd have to review that. But yeah, so here you're finding the null space. The null space is parametric, as you can tell, when you multiply the... Oops, that was weird. I don't know what just happened. When you multiply the... Okay, so the null space isn't one single vector, ever. It's a direction. So, I mean, arguably you could say that, yes, it is a single vector, but a vector exists as a direction with magnitude. So, you know, anything along this is actually like a bivector, sort of. This is anything within this plane. You have two free parameters. You have two dimensions, right? And so anything within the two-dimensional plane that these four-dimensional vectors, so these vectors are pointing in particular directions, right? And they're embedded in 4 space. But they form a plane because you only have 2 of them. And so you have 2 free parameters. So there's a whole plane in this hyperspace, this 4 space, that gets multiplied by 0. It goes to nothing, right? And anything that you can multiply, you know, any constants by these, and no matter what, those would be elements of the null space, meaning that you would multiply it by a and it would give you 0. This is kind of like, I don't know if you remember from differential equations, but the homogeneous solution. So same sort of thing going on. When ax equals 0, then that solution also, it gives you a parametric solution, and that parametric solution also is something that will pop up in other solutions, right? So that was problem 4, I guess. That's weird. That's really weird. I don't know what problem that is. Anyway, I'm going to start the next video.